Hi guys, I'm Courtney Keiser, and today I'm going to be telling you about my research on mechanically optimized aortic stent grafts. So what are stent grafts? Right here, look up right in the corner up here. They're a metal frame-enforced fabric that is used to prevent and repair a fatal failure of the aorta due to aneurysmal rupture or traumatic injury like a car accident. And what they do is they take this stent graft and they crimp it down really small, and they'll attach it to a catheter. And it's inserted into your groin and snaked up your aorta to the site of damage, where then the surgeon is able to deploy that stent graft, and it pops open from the top to the bottom to allow the blood to be redirected across the damaged site, therefore repairing the aorta. And this technique is endovascular repair, and it is recommended over open heart surgery due to improved short-term outcomes, but reintervention still remains high. And the reason for that is these stent grafts are made from a very stiff fabric, and that drastically changes the blood flow and the pressure within the aorta, which has been shown clinically in humans. And we just recently did a pig study with this. It's been shown to increase the mass of the left ventricle, damage coronary vasculature. So we've got this stiff material that we're sticking in our aorta, and the aorta is much more compliant than this stent graft. So the aorta tries to minimize this compliance mismatch by breaking down elastin, which is what gives it its elasticity. And in a sense, you're accelerating the vascular aging in your aorta. So this isn't very good. And so our research lab is focused on the development of a compliant stent graft that minimizes that compliance mismatch and will hopefully minimize these negative side effects and improve outlook for patient treatment. So our objective is to develop a stent graft that has mechanical properties that are similar to the aorta. And then to understand that a little better, I wanted to explain how the aorta behaves. So if you look on the left over here, on systole, the left ventricle, it's going to contract. It's going to push blood into the aorta. The aortic valve opens, and then the blood goes into the aorta. The aorta is going to distend and store stroke volume, which is just the blood volume per cardiac cycle in the aortic wall. Then on diastole, that left ventricle is going to relax, and that stored stroke volume is going to be released and pushed downstream to distal organs that need that. And if you look up here in the top right corner, this is a pressure versus time waveform of what's happening in the aorta. And you can see on systolic pressure, you see this nice peak up to 120, and then on diastole, this slow decay in the pressure. And this effect, or this phenomenon, it's known as the Windkessel effect, and its purpose is to blunt peak pressures, and it kind of acts as a cushioning effect for the heart and the aorta and those downstream organs to protect them from too high of pressure, and then also to allow for this continuous blood flow to the vasculature. So if you look on the right, this is a simulated Windkessel effect. We've got this compliant material that's able to distend and recoil, and you can see the pressure waveform for that is it peaks and there's a slow decay, and we're able to get this nice continuous flow. But on the left side, with no Windkessel effect, if we have a stiff material, we get this very sharp peak in the pressure, and then it kind of flat lines, and that generates this very spurty flow, which is not what we want out of our stent graft. So our approach, first making the fabric, I use a technique called electrospinning. This just utilizes a high voltage electric field to draw a charged polymer to this grounded collector rod. And by controlling the process parameters and the different types of polymers used, you can tune the mechanical properties of your fiber material to match that of the aorta. So once I've made my fiber material, I test it on a biaxial testing machine, which just stretches the material in the X direction and the Y direction, and then it measures the force that's necessary to stretch that material. And then I'm also lucky enough to get human aorta samples donated to our lab, where I can actually test aortas of different ages and test their mechanical properties and try to tune my fabric to those of the aorta. Now, once I got the fabric done, now I got to develop these stent graft rings. We have developed in our lab these different metal plates that have different geometries that we have made ourselves to make the stent rings. We use a nitinol wire, which is a shape memory alloy. So once I wrap my nitinol wire around these different geometries, I put it in this fluidized bath, which is set to 500 degrees Celsius. And once I remove it from the bath and take it off of this plate, it retains the shape that I set it at. And so once I've made the geometry, I wrap them around these cylindrical tubes, and I'm able to set the diameter. of these stent rings. And then we've also played around with this middle design right here, was something that we developed ourselves in our lab to try to improve the stent graft ring, because we're trying to make these rings so they're able to expand and recoil, which the current stent graft rings do not do that, because that's not what the grafts are meant to do. So some results, I was able to create a compliant fabric with a nonlinear stiffening response under increasing load. So my nanofibers are over here, and you can see if you stretch it in the X direction or the Y direction, it has a different response under the load, which is very similar to what we see in arterial nonlinearity of healthy human arteries. This was a 33-year-old thoracic, which is just the upper part of the aorta that I had tested. And you can see if you stretch it in the longitudinal or the circumferential direction, you get a nonlinear stiffening response on increasing load. And so here are some of my prototypes. Once I have made one, I mount it on this pulsatile flow system, and I test it for durability, and I test it to see if those stent rings will fracture. And then also the fabric is a biocompatible hydrolysis-resistant polyurethane. I forgot to say that on the last slide. So this stent ring geometry here kind of follows what commercial stent rings, the geometry they use. And once we would mount this on the pulsatile flow system, it was very notorious for these stent rings to fracture, which kind of propelled us to develop our own stent ring geometries. And the nitinol number 2 and the polymer number 1 designs, they have these longer struts, which we chose that design to allow for that radial expansion. And this design also has these smaller struts to kind of limit how wide the diameter can go. And this was just a prototype, or for the polymer, we developed that plate that I showed you previously, and we're trying to optimize making those stent rings. So hopefully in the future I'll be able to have a stent graft with nitinol rings like this. But the next slide, I will show you my results with the middle nitinol number 2 stent ring. So you can see on the left, I've got both of these hooked up to a pulsatile flow system subjected to the same stroke volume. In the left, you don't see any diameter change over time. This is the commercial stent graft. Whereas on the right, my nanofiber stent graft, as you can see, is able to distend and recoil cyclically. I measured the diameter change on the left, the middle, and on the right. And I was able to continue this for 7 days without any delamination, no stent fracturing, and no damage whatsoever. So that was really promising results for that. And so in conclusion, stent grafts that preserve the elastic properties of the aorta, they show great promise for preserving the Windkessel effect and the development of a stent graft with mechanical properties that are similar to the aorta. And this could result in better clinical outcomes for trauma patients and for aneurysmal patients to avoid complications such as that left ventricle mass increase. We're going to decrease that compliance mismatch between the aorta and the stent graft, so the adverse aortic remodeling will go down. And that would be able to have safer pressures in the heart, the aorta, so you'd be minimizing that coronary artery damage and minimizing that damage to distal organs. And then my future work will focus on optimizing the mechanical properties of the stent graft fabric, improving stent ring fabrication, and then developing pulsatile flow circuit parts to measure the pressure and the diameter change in real time, and then also the flow rate. And I'd like to thank NIH for the funding of this research, and my advisor, Dr. Kaminsky, and collaborators, Dr. Maletskis, Dr. Desayotova, and Dr. McTaggart. References.